All right, welcome back. So today we are going to solve a fundamental array question. Now let's get right to it. So the question is sort colors. Now let's read the question. Given an array with n objects colored red, white, or blue, sort them in place so that objects of the same colors are adjacent with the colors in the order red, white, and blue. And then just to make it easier, you're going to use the integers 0, 1, and 2 to represent red, white, and blue. So here's an example. If you have this array, then what you want to do is you basically want to sort it, and then you'll sort it into 0, 0, 1, 1, 2, 2. All right, cool. So let's see, a rather straightforward solution is a two-pass algorithm using counting sort. Interesting. Could you come on? Okay, cool. So basically, let's look at the problem right away. Okay, so now imagine we have this array. We have 2, 0, 2, 1, 1, 0. So that is the array that we're working with. And then what we want to do is we want to transform this into 0, 0, 1, 1, 2, 2. So I want to talk through a few solutions and then talk about why that's good, why that's not good, and stuff like that. So here it actually has a follow-up that says like, okay, imagine there is a straightforward way where you can just have a two-pass algorithm where you just count them because there are 3 colors, right? So what you can do, what they're saying is that, so you can have a hash map where 0, and then you get 1, and then also 2, right? This is your hash map. And then basically what you want to do is you want to go through this array, going back to the original array, and then you're going to go through it and count how many there are. So for example, once you see 2, you're going to add 2 here, first 0, and then 0, this becomes 1, this becomes 1, and then once you see 2, this becomes 2, you see 2 1s, this becomes 2, and then 0 becomes 2. And then all you have to do once you get this like array, let me rewrite this more clearly. So basically you found 2 0s, 2 1s, and 2 2s. Then it's very easy because all you can do is you're gonna rewrite this array, or like you're gonna rewrite this array, and then you're gonna replace these guys by these numbers, like for example 0, 0, because you have 2 zeros, and then once there are no more zeros in your hash map, you start doing 1, 1, and then 2, 2, right? So very simple, you know, just utilizing the hash map. So like I said, we rewrite it. It's like 1 here, it's like we get a 0, this becomes 1, and then you could use another 0, this becomes 0. And then now you have 1s, you have a 1, this becomes a 1. And then you have you take that 1 off, becomes a 0. And then now because there's 0, you have 2s. And then that's pretty much the answer, right? Perfect. So what's the time complexity of that? The time complexity of that is O of n. You do it twice. The first time you do it is to do your hash map. So the time complexity is O of n, and then space is O of, we'll say 3, because it's like a hash map of 3 elements, which is basically constant time. Cool. So, I mean, there's another really brute force way is you could literally just sort it. You could just use any sorting algorithm and it will sort it in place, and then you'll get the result you want. But that would give O of n log n, which is way slower, right, if we sort. So is there a better way of doing this? Is it possible to not use a hash map and only using 1 pass? Well, it actually is. So these are kind of like the fundamental array techniques that you would use, is by having multiple pointers and understanding how you're passing through the array, and having these pointer mean certain things. So I know it's kind of vague now, but let me try to explain what it is. So let's redo this. Let's use some colors. It might be even more useful if you see some colors. All right, so now that I've drawn it with colors, I'm gonna show you how you can use 3 pointers to do 1 pass so that you can sort all of these guys. You can partition them. Like remember, it's not exactly sorting because all of the zeros are the same and all of the ones are the same. There's only 3 numbers. So what you can do is the following. So imagine you have one pointer, this one. This pointer, let's call it a P, let's see, what should we call it? Yeah, let's call it P0. All right, so P0, what it is it's like the rightmost boundary of 0. Rightmost boundary of 0. All right, and then we'll have another pointer, which is, we'll start it also over here. Let's call it P1. P1 is, let's call it like the current index. The current index. So what that does is it looks at the current index and does some computation. I'll talk about this later. And then P2, we'll point it here. P2. So then P2 would be, we could mostly call this as the leftmost boundary. Boundary of 2, right? So the technique here is that you know that these two pointers, the extremities, P0 and P2, they are going to be the extremities of the P0. Anything before P0, you know it's going to be zeros. Anything after P2, you know it's going to be 2. And everything in between, you don't know yet, right? That's what P1 does. P1 looks at it, and then depending on what they see, they're going to swap the numbers out, right? So let's kind of do one exercise to make it more clear. So imagine first you have these guys, right? So right now, P0 is undeclared in some ways. Like you don't know if it's P0 or not. So, and then also P2, you don't know if P2 is anything. So what we do first is like, okay, P1 is our current guy. So P1, we see number 2. So number 2, as you can see, if it's number 2, then we want to swap it with P2, right? So let's swap it with P2. So then now this will become, yeah, let's swap it with P2. So then this becomes 0, this becomes 2. So now this becomes 0, and then this becomes 2, right? So now we successfully swapped it, and what we want to do is now we want to move, there must be a better way of doing this. Now we have P2 right here, oops, P2 right here, and then, yeah, so now you see that all of these guys, we know that it's P2, and all of these guys, you know it's zeros, right? And then the same thing, we continue, right? We just swapped it. And first of all, here, we still don't know that it's P0 yet. Like it just happened coincidentally. So now P1 continues, and now P1 is here. It sees that it's a 0. So what's gonna do, it's gonna swap with P0. So we're gonna swap, and then coincidentally, they're both 0, so that's great. So once we swap, what we wanna do is we wanna increment both P0 and P1. Right, so now this becomes P0, and this is P1, right? And what did we say before? If we see a 2, then we're gonna swap with P2, so we're gonna swap with this guy, right? So now this becomes P1, and then, here it becomes 2. And then this guy goes over here. P2. So now you know everything after that are 2s, and then everything before that is 1s, right? And then here, you know that everything after is 0s, right? And then if you have P1s, you continue because P1 is in between 0s and 2s, and then you'll stop once P1 hits P2. So we're gonna have another iteration where P1 goes here, it's gonna see it's 1, it's gonna go again, it's gonna see that it's P2 there. So that's pretty much what you wanna do, right? So the reason why this works is that every time you have a 0, you know that you're gonna put it all the way to the back, and you know that everything before P0 are going to be 0s. And if you see a 2, you're going to put it all the way to the right, and you know that if it's on P2, everything to the right is 2. So these are already all done and partitioned for you. And then for 1s, those are the only ones that you don't do anything with it. So the only thing that can happen is that at the end, only 1s are in the middle, right? In some ways, you could think of this problem as like you're going through the array and then you're putting all the 0 in the beginning and then you're putting all the 2s on the side, and then whatever is left, you just fill it with 1s. That's exactly the same thing that we're doing here. So, all right, let's code this up. So how do we do that? Now, remember what we said about the different cases. There are 3 cases, right? Let's start by initializing our pointers. So like we said, P0 would be on index 0, and then current would be also index 0. The current would be the P1. Let's call it P1 so it's easier to remember. And then P2, it's all the way at the end. It's length of nums minus 1. All right. So now, what did we say before? If ever P1 becomes P2, then we stop. So as long as P1 is smaller or equal to P2, you continue. Now, there are 3 cases. If the number that we see is 0, right, that's one case. And then the other case is if the number is 1, right? And then also the other case is basically 2, then something happens, right? So, as long as we do these 3 cases, and then we're pretty much done. And then what you want to do at the end is you don't really return anything, because here you just want it to be sorted. So if you see a 0, what do you want to do? You want to swap with P0, right? So that's how you do it. You do nums P0 and nums P1, and then you swap them. So how do you swap them? You just do nums P1. This is just a short form way of doing swapping on Python. P0. So basically you swap them, right? And then after you swap them, what do you want to do? You want to increment both of them. So +1 and P1 +1. All right, so if it's 1, what do? Nothing, you just keep going. So P1 +1. And then else, which means if you see a 2, what do? You want to swap with pointer 2, right? So nums P0, nums P2, nums P2, nums P0. All right, so then you've successfully swapped them. And what do you want to do? You want to decrement P2. All right, cool. And then that's pretty much it. All right, so the reason why for P2 we do -1 and then we do not increment P1 is because once we do swap the P2, it means the 2 goes into P2, and then whatever P2 has, it's going to go into P1. But you don't know if it's a 1 or a 0, because if it's a 0, then you're going to have to swap with P0 again. So you don't know. You don't know yet. You haven't seen that yet. It's basically an unclassified a number. And then the reason that in here for P1 that you need to increment both P0 and P1, because everything after P1, or sorry, everything before P1, you've already seen it. It's already been classified. It's always going to be guaranteed either 0 or 1, right? Because the pointer of 0, you know that everything on the left is 0, and everything after it's either 1. I mean, it has to be 1. The reason is because we've already seen all that. If there was a 2 before, you would have swapped it already with number 2. So in some ways, the way P1 moves is you know that as long as it moves, everything behind P1 has been classified. Everything is already perfect, right? You don't need to move it anymore in some ways, right? So that means everything is either 0s or 1s. So if ever you encounter a 0, you're just going to be swapping with the 0, and it's guaranteed to be it's going to be a 1, because like everything that's before 0, it's all 0s, and everything after 0 until 1, P1 is always going to be 1. Anyways, so that's pretty much it. So I hope that was helpful, and yeah, this is a pretty common technique for manipulating arrays, partitioning arrays. So yeah, thank you. And oh wait, let's talk about time complexity. So time complexity here is very obvious. It's O of n. It's linear because we only do one pass. And then in terms of space complexity, it's O of 1 because we do not allocate any new memory. All right, cool. Thank you so much. See you in the next one.